So in this next section, we'll take a look at estimating the population mean, which again means we're going to be looking for a confidence interval given a sample mean. Now, this specific situation we're going to be in is, I would say, kind of a real-life type of situation where you generally are going to not know your population standard deviation if you're not knowing your population mean. Well, as soon as you don't know your population standard deviation, the z-score formula switches or changes slightly to where you have to use S instead of sigma. But what also happens there, without getting into the nitty-gritty detail, is we're not going to be allowed to use the official normal curve, which means we can't use something like inverse norm. What we end up with is something that was referred to as the student t-distribution, or what I'll call the t-distribution, which is something that's very similar to the normal curve. And the properties down here, you'll notice many of them are exactly the same as we had for the normal bell-shaped curve. But the idea here is that it involves something called a degrees of freedom, where dependent on your sample size, the exact distribution of that normal curve or close to normal curve can be altered, can change slightly. So because of that, we will talk about degrees of freedom, and it is this specific value of 1 less than your sample size, n minus 1, and we have, again, just slightly altered looking what we'll call a t-score formula. It's really a z-score formula with S instead of sigma. But the idea here is we cannot use inverse norm anymore. So because of that, we'll have to use a chart of information instead. So again, you can read through these details. It's very similar to our bell-shaped curve, but I want to get to what's different. What makes this problem different than what we would have seen back in chapter 7. So to estimate the value here for the population mean, we'll be using t-values. It's still the same idea, same picture. We will still draw a bell-shaped curve because the t-distribution is very close to a normal curve. It basically looks the same. But when we talk about this value, trying to find this boundary line with a alpha, whatever area to its right, notice we're calling it t sub alpha now instead of z sub alpha. The difference is we use a chart to look it up. So if we want a t-value, such that specifically, let's say the value to the right, the area to the right is 0.2, and it says assume 10 degrees of freedom. Now that would mean that the sample size for this, whatever it was, is 11, right? So to do that, and here's just a small piece of a t-distribution chart. We'll get to a fuller one when we get to the problems. But all you do with a t-chart is you look up the area in a right tail up on the top, right? You'll have this row up here, and you'll have your degrees of freedom row along the left-hand side. So it's important to notice this is not n, this is your degrees of freedom. So for this example where n was 11, we would look at the degrees of freedom of 10, we would look at the alpha, the value area to its right of 0.2, and we would see that those two intersect right there at that 0.879. So that's telling us that our t of 0.2, or t sub alpha in this case of 0.2, is going to be that 0.879. Now again, that is not a probability. That is a t-score, which is just like a z-score. Notice these values definitely can be in the 1s, 2s, 3s, and even bigger potentially because of the weird distribution at low sample sizes. So that is not a proportion. That's not an area under the curve. That is a z-score, but it's a t-score. That's the only difference. That's what these numbers in this chart are going to represent for us. Okay? So with that said, we get to the specifics of what we need in order to construct a confidence interval for mu. Okay? Now, these first couple are just kind of given. They're going to come from a simple random sample. Again, the idea of having a sample size small enough that it's not too close to your population size. But we get to this one, and this is kind of, if you want to call it the important one. We need to know that either the population is normally distributed, or we have to have a sample of at least 30. One or the other, right? One of those two things has to happen for us to even be allowed to use a t-distribution to create these confidence intervals. But from there, if you look at the formulas, it's very similar to the proportion one. It starts off with the point estimate of x bar, and then adds or subtracts the same quantity. Now, in this case, we're looking at t sub alpha over 2, and then times s over root n, standard deviation of the sample divided by square root of the sample size. So that's the calculation. Those are the formulas. Let's go ahead and introduce the problem on this page, and we'll actually jump into the work on the next page, so we have room. Construct a 99% confidence interval for the population mean weight of pennies minted after 1982. And here's our sample. Okay, so we took a sample of size what? 2, 4, 6, 8, 10, 12, 14, 16, 17. Let's point that out. Now, this thing right here, this little detail, this is something that we kind of glossed over back in chapter 7. I gave you a page of notes on it. All you need to know about this is with small sample sizes, if you do not know whether your population is normally distributed or not, you can use a Minitab plot. And all you need to know is that when you look at this plot here, all these dots that represent the data values should be between these two dotted curves. As long as they're in between these two, we can use this to say that our population is approximately normal. So we didn't have it in the initial information, but with this representation of this data set, this sample, we can say that our original data set is normal. So we don't have a sample size above 30, but we now have this. Not because we were told it, but because of this guarantees it for us. Okay? Now, the issue is we were given the sample information, but we don't have a sample mean or sample standard deviation, right? We don't have a X bar or S. So I want to make sure everyone knows how to use their calculators to find that rather than having to do it by hand. So you want to go to the Stat button right here, and the very first option is Edit. That gets you to the lists. So we're going to enter all those numbers into that list there. When you get to the bottom of that list, you'll notice one quick thing here, just to at least know you entered the right number of values. You'll see this L1 and then 18. That's telling me that if I entered a data value here, that would be on the 18th spot. And so that means that I do have 17 values typed in there. So we'll just hope that they're all entered correctly. In fact, it looks like one of them might not be. Oh, nope, it is. Okay. So once you've got those values entered, you want to go back to your stat key again, over to calculate, just arrow over to once to the calculate, and one var stats. If you click enter, it pops up on your home screen and it will default to grabbing that list in L1. So if you put your list in L1, you got it. Otherwise, you do need to use the second button and come down here and pick whichever list you just typed your data values into. But I can say enter again. And the two big things we need are the X bar right there, the value of the sample mean, and the S, right? We get both the population and the standard and the sample standard deviation. Remember, they're different because of the different formulas slightly, so we'll need that value for S. So we now know that X bar is 2. If I go 3 places here, 464, and the sample standard deviation, I'll go 4 places, is 0.177. Okay, that's the information we'll use on what is officially the next page here of your notes. I'm going to leave that information up there if possible. Actually, let's copy it down. So we need, for a sample mean of 2.464, sample standard deviation of 0.0177, we want a 99% confidence interval from our sample size of 17. All right, so let's determine our t-score, our t sub alpha over 2. Now, to do that, let's point out first that if we have a 99% confidence interval, that means alpha is that last 1%. So alpha over 2 is half of that, so 0.005. So on the official t-score here, t-score chart, it goes much lower. So I do have a value of the 0.0005. And we can use that n of 17 to say the degree of freedom will be 16. So we're using degree of freedom 16 with an alpha of 0.005 So there's 0.005, degree of freedom 16, come over, down, and looks like 2.921 will be our t-score for this confidence interval. So you simply cross-reference the area in the curve, or area under the curve in the tail. So just in the alpha over 2 with degree of freedom to get your t-score. From there, we just throw it into our formula. So again, our formula was x bar. I'm going to think of it as plus or minus t alpha over 2 times s over root n. So we have our x bar, 2.464 plus or minus would be 2.921 times s over the square root of, and make sure our sample size gets in there, and then we'll see what we get. Again, I'll do just the margin of error portion, everything to the right of that plus or minus. So I'm getting 2.464 plus or minus 0.013 if I round. And so with that, oops, off the screen there. So with that, we can say our lower bound would be 2.451. Our upper bound is 2.477. And has pretty much the same interpretation, just same sentence structure. We would say we are 99% confident that the population mean weight of pennies minted after 1982 is between 2.451 grams and 2.477 grams. And so, lastly, kind of like in the last section, we can also approach these questions not by constructing the interval, but by asking again for that sample size. What is the sample size needed for a certain level of confidence and a certain margin of error? Same exact idea as in 9.1. The only thing here is we do need to use or have access to prior knowledge. We need the population standard deviation. That's required to jump in here. Kind of like we needed a value of p hat for 9.1, whether it was from previous data or we just used 0.5. This we have to have a value or at least an assumption for the value of sigma, the value of the population standard deviation. So we want to find how large a sample would be required if we wanted to estimate within, so there's again, the within is your margin of error with a 99% confidence and sigma of 0.02. Notice here, when you're doing this, we are going to be using the normal curve again. We're going to be using inverse norm to determine this. Again, it kind of boils down to we're assuming we have this. It's when you don't have this, back on the last question, when you don't have your population standard deviation is when you're stuck using that t distribution, which is why we had to use the chart. So to find our z alpha over 2, to find that, we have a 99% confidence level. So again, what that means is you've got 99% confidence. So alpha is that 0.01. So half of that is 0.005. So these tails are very tiny and have 0.005 as the area in them. And so to find that boundary, we'll need inverse norm of area to the left. So if it's 0.005 to the right, it's 0.995 to the left. So inverse norm, 0.995 is 2.576 for our, and it's supposed to be a z, for our z-score. And then we can plug everything into our formula. So sample size is the z-score, 2.576, times our assumed population standard deviation of 0.02, divided by the margin of error. We want to be within 0.005, and then that whole thing should be squared. And that's coming out to a 106.17, but like last time, no matter what here, being a sample size, we're going to round up and say we need to sample 107 pennies.